In this video, we will talk about binary classification and logistic regression. Let us recall that task of supervised learning divides into two categories. Regression, when the data labels are all continuous, have continuous values, and when labels are discrete, this task is called classification. So here it is represented in more formal way. When the mapping function is continuous value, we call it regression, and when it is discrete value, we call it classification. The simplest example of binary classification is to classify the emails into two categories, spam and not spam. Let us recall what we considered in one of the previous videos, how the linear regression works. In the simple univariate example, when we have just one variable, car weight, we can predict the consumption of the vehicle by calculating the parameters of the line, which approximates our data points in the optimal least squares way by using the mean square criterion. So we are building a line which approximates in the optimal least square sense our data points, and we can use this line to predict the future observations. Okay. The question is, why cannot we do it? Why cannot we apply the linear regression to classification task? In fact, as we will see, we can do it, but it will not produce the desired results. Okay, let us consider some practical example. We have 94 data points, which are represented here on this graph. In red color, there are data points which correspond to the decision 0 or false, and the blue points correspond to the decision 1 or true. In fact, these data are connected with the information about the cars, which we are using in one of our previous examples, but we will talk about it in more details in one of the next videos. Okay. We have this set of data points, and the question may arise, maybe how to classify, can we classify future observation? We see, by the way, that these data are slightly intersecting, so we cannot obtain the perfect classification, of course, in this case. And for example, we can build a line. We can try to build a line which will approximate this point and use this line for future predictions. Okay, and let's try to do it by calculating the parameters of linear regression. I need to remove this line just a moment. Okay. Okay, so here for these data points, I will run the notebook. Yes, by calculating the parameters of linear regression, and we see that we can approximate we can construct line which approximates our data points. And for example, we can see the intersection of this line with the level 0.5 like probability. Yes, and the data points which are to the left of this intersection point are classified with decision 0, and they are classified with decision 0, and the data points which are to the right of this intersection point are classified with the decision y equal to 1. So yes, but of course we can see that this line, of course, this linear regression produces values larger than +1 and less than -1, which is not very good. Of course, in this situation here I outline several drawbacks of this approach. It is not easy to apply regression model in this case because it produces the values outside the range of 0 and 1, 0 to 1. But there is one more important disadvantage. I will show it. Let us add 1 point to our data. For example, I will add x equal to 30 to our data, and our data points now look in the following way. Yes, you recognize them. We added 1 point with decision 1 for the x equal to 30. Okay, let's see how our linear approximation changes in this case. Will it recalculate? Yes, it recalculated. You see now how the our line, how it shifted. Yes, and almost all of the data points are now to the left. Of the intersection point of this line with the level 0.5. So, and obviously in this case we have very large classification error. 0.75. 75% of the points are wrongly classified. And let us recall, I did not mention it above, that the classification error was, when we did not introduce this additional point, it was 0.12. I will show it. Where is it? Let us recalculate it in. I did not make an accent that. So, yes, these are our original data points, and if we perform linear regression, then the classification error is 0.12 or 0.13, but it increases to 0.75. Yes, we add just one additional outlier, just one additional outlying point. Okay, so what should we do? One of the main disadvantages is we told that the linear regression produces the values which are outside the range of 0 to 1. So we need some function. Which will squeeze or which will map the region from -infinity to infinity to the interval -1. No, not to -1, but to 0, 1. It's my mistake. I will correct it. You see here, it should be 0. 0 to 1 to this interval. Okay, what function should we use for this purpose? The one of the most popular choices in this case is a so-called logistic function, which is of the following form, which looks like this. It's denoted by Greek letter sigma, and it's 1 over 1 plus exponent of minus z. Sigma of z is 1 over 1 plus exponent of minus z. So we can plot the graph, of this function here on the plot below. We can see how this function looks. So for the negative values, it produces the magnitudes of which are very close to 0. Yes, you can see this example. For the values which are larger than 0, much larger than 0, it produces almost 1, probability almost 1. And of course, for the value 0, this sigmoid function, which is also called sigmoid function, this sigmoid produces a value 0.5. So both decisions are equiprobable. They are both equiprobable. So now we'll look how this logistic function, this sigmoid function, approximates the data in our example. I will run the notebook. It calculates the optimal values of parameters W and B, and we can see here this approximation. So this sigmoid function, it tends to approximate in a step-like fashion our data points. And we can see that the ratio decreases, the classification error decreases to 11%, from 13 to 11%. But the very important point is that if we add this outline point, which destroyed almost everything, in the case of direct application of linear regression, let's do it again. I'm adding this point. Yes, you see, outline point. As we can again observe, destroys the application of linear regression. We have the error 0.74, but when we apply sigmoid function with correspondingly calculated parameters, we now have a classification error. See the plot redisplayed here, and classification error is again 11%, just 11%. So it didn't change. In fact, it became even a little less, as far as I remember. Okay, just 11%. So this approach is more stable. Using sigmoid function is more stable than the application of direct linear regression. Let's look again at this sigmoid function. Here I prepared a little slider showing it. It has two parameters. The shift B and the weight coefficients W. In our next video, we will look how we can calculate these parameters. So shifting this B, parameter B, produces shift from left to right. Yes, you see of this sigmoid function. And parameter W, weight coefficient W, changes the speed of change of sigmoid function. So the higher is W, the more it looks like stepwise function. The closer W is to 0, it looks like almost like a not a straight line, but it's much more smooth. And correspondingly, when we cross the 0, it changes. Sigmoid function changes its direction. So it is very flexible. It's very flexible to model the changes in our data points. Okay. So this sigmoid function, as we saw in this video, we can produce nice results for modeling changes in our data to be classified. We'll talk about more in the next video, and also, of course, we will consider how to calculate these parameters W and B of logistic regression. So in this video, we considered how to apply a very simple example, the method of logistic regression to the classification of one-dimensional data points, and why it has advantage or disadvantage over the direct application of linear regression. Thank you very much for your kind attention.